Picture a brutally hot afternoon in the late 1990s. We're in Albuquerque, New Mexico, standing in the dusty yard of a company called ZomeWorks. The desert sun is hammering down without mercy, turning the air into a shimmering veil of heat. Look closely, and you'll notice an eccentric man with graying hair and the sun-darkened skin of a welder, standing beside a small, ordinary-looking shed the workers call the Andy Shack. His name is Steve Baer. He isn't carrying a modern air conditioning manifold or an expensive cylinder of refrigerant. Instead, he is carefully hanging recycled plastic hospital IV bags filled with ordinary tap water along the frame of the shed. He strips the little building down, rebuilds it, and installs one experimental system after another, all in pursuit of a single radical idea: a building that could heat and cool itself using absolutely no outside power. No connection to the grid, no noisy compressors, no fans, no complicated electronic sensors. What eventually came out of that dusty yard was patented, entered continuous commercial production, and for more than 2 decades quietly helped keep critical infrastructure operating across 6 continents. It has kept telecommunications battery banks cool inside steel enclosures in places like the Sonoran and Sahara deserts, protected by little more than a reservoir of water and a lid that sends heat directly toward the night sky. And now, that patent has expired. The idea belongs to the public. Anyone can legally build it. But that raises a question worth thinking about. If this technology is reliable enough to protect million-dollar telecommunications sites in 115-degree desert heat without consuming a single watt of electricity, why has nobody ever sold one for your bedroom? Why isn't there a residential version sitting on the market today? The answer is not some hidden corporate conspiracy or secret government buyout. It is far more interesting than that. A collision between unforgiving structural mathematics, the brutal physical reality of water, and competing economic business models that helps explain why so much of our daily comfort is still rented from the electric grid. Today, we're going to take apart the cool cell, understand the physics that allows it to work, examine why it never reached ordinary homes, and uncover the simple, low-cost principles hidden inside this expired patent that you can borrow to cool your own home for pennies. Part 1. The Mathematician in the Junkyard. To understand how a steel box filled with water could compete with a multi-thousand-dollar HVAC system, you first need to understand the mind of the man who created it. Steve Baer was not a typical mechanical engineer. Born in Los Angeles in October 1938, Baer followed an unusual, wandering path through life. Amherst College, UCLA, an American Army base in Germany, and eventually the prestigious ETH in Zurich, Switzerland, where he studied mathematics. Somewhere along that journey, Baer worked as a welder in a metal shop. And it was there that the clean, elegant geometry of 3-dimensional space truly captured his imagination. He became fascinated with polyhedra, complex, many-sided forms capable of dividing space with remarkable strength while using surprisingly little material. When he returned to the United States in 1966, Baer became involved with the artists and counterculture builders of Drop City, an experimental commune outside Trinidad, Colorado. Drop City was a playground for unconventional, low-cost architecture. The domes and polyhedral structures rising from that barren land were not built from expensive lumber or factory-made panels. Baer and the other builders went to local junkyards, bought discarded automobiles for a few dollars, cut away their hoods and roofs, hammered the metal flat, and bolted the pieces together into beautiful geometric structures they called zooms. It was architecture assembled almost entirely from materials society had already thrown away as worthless. Baer had little patience for people who only theorized. Looking back on early meetings of the International Solar Energy Society, he observed that people were talking endlessly about sophisticated multi-million-dollar tracking collectors and exotic absorbing surfaces, while almost none of the men doing the talking had a functioning prototype sitting in their own backyard. Baer went home and built one. In Corrales, New Mexico, he constructed his family home, the famous Zome House. Across the entire south-facing wall, he stacked 90 55-gallon steel oil drums. Each drum held 53 gallons of water. He painted the outward-facing ends black so they could absorb the winter sun, while the inward-facing ends were painted white. Outside the drums, he installed 2 layers of glass to trap heat. He also built hinged insulating panels clad in aluminum that opened during the day and closed again at night. Baer called the system the drum wall. And through the freezing winters of New Mexico, it heated his home using nothing more than thermal mass and natural convection. Keep those 90 oil drums in mind, because what they represented physically would eventually provide the clearest explanation for why most of us are still paying an electric bill to stay cool. Part 2. The birth of the cool cell. By the 1990s, Baer's attention had shifted. Instead of focusing mainly on keeping houses warm during winter, he became increasingly interested in keeping them cool during summer. Back in the ZomeWorks yard in Albuquerque, the humble Andy Shack became his ultimate laboratory. It was about as unglamorous as an experimental building could possibly be, yet what happened there may have been far more important than its appearance suggested. Baer was fascinated by a simple physical reality. The night sky is not merely empty air above our heads. On a clear night, the effective temperature of deep space is extraordinarily cold, far below the temperature of the air near the ground. That means the open sky can behave like an enormous heat sink, ready to receive thermal radiation from surfaces that have a direct view toward it. The challenge was finding a way to capture that nighttime cold and preserve it through the scorching heat of the next afternoon. Baer realized that if you combined a body of water with an unobstructed view of the night sky, you could create a natural cooling loop that switched itself on and off without machinery. His experiments on the Andy Shack eventually led directly to the cool cell. In December 1992, he filed a passive cooling patent assigned to ZomeWorks. Open a commercial cool cell, and you find remarkably little inside. At the bottom of a heavily insulated steel enclosure sits a large reservoir of water. Built into the lid is a flat-plate radiator. 2 pipes connect the 2 components. One pipe runs from the upper portion of the water tank to the high side of the radiator. A second pipe runs from the low side of the radiator back down to the bottom of the reservoir. That is essentially the entire machine. No compressor, no pump, no valves, no electronic control board. Yet place it in the desert, and it begins moving heat out of the enclosure according to a remarkably predictable natural cycle. It was a simple but durable marriage between 2 things: a body of thermal mass and an unobstructed line of sight to the sky. Part 3. The secret physics of the cool cell. So how can such a simple plumbing loop take the place of a roaring, vibrating mechanical compressor? The answer begins with one extraordinary property of water: its enormous specific heat capacity. Water can store more heat per pound than almost any common material we encounter in ordinary construction. Raising the temperature of 1 pound of water by 1 degree requires roughly 4 times as much energy as raising a pound of aluminum by the same amount, and around 9 times as much as structural steel. A large tank of water therefore acts like an enormous thermal brake. Temperature changes happen slowly because so much energy must be absorbed before the water becomes significantly warmer. But a thermal brake can only delay heat. Eventually, that heat still has to go somewhere. That is where the radiator in the lid and the natural convection loop become important. During the day, intense desert sunlight strikes the steel enclosure. At the same time, the equipment inside, such as a bank of charging batteries, produces its own waste heat. The reservoir of water at the bottom absorbs that energy, gradually warming and expanding slightly as its temperature rises. Because warm water is less dense than cooler water, it naturally rises toward the top of the tank. From there, it enters the upper pipe and moves into the radiator built into the lid. Then night arrives. This is where the system truly comes alive. The lid of the cool cell has a clear, unobstructed view of the open night sky. The radiator begins releasing infrared energy through the atmosphere and outward toward the enormous cold sink of space. As the water inside the radiator gives up its heat, its temperature falls. As it becomes colder, it also becomes denser and heavier. Gravity now takes control. The colder, denser water flows down through the lower pipe and returns to the bottom of the main reservoir. That downward flow displaces warmer water near the top of the tank, pushing it upward through the other pipe and into the radiator. The cycle begins again. And it continues automatically through the night, driven entirely by the density difference between warmer and cooler water. By morning, the reservoir has effectively become a large store of naturally collected cold. Then, as the next hot day begins, that chilled thermal mass serves as a shield. It absorbs incoming heat and keeps the inside of the enclosure cool. In that sense, the cool cell is not really a conventional cooling machine. It is more like a scheduling machine. It takes advantage of the natural temperature difference available between 2 a.m. and 2 o'clock p.m., stores that advantage, and saves it until the heat of the day makes it valuable. Part 4. 39 Degrees of Magic and the Invisible Explosion, Vent. The deeper you examine Steve Baer's designs, the more you begin to see how the physical behavior of water itself functions almost like an automatic control system. In an ordinary HVAC system, you need thermostats, control boards, and motorized valves to protect equipment from freezing during winter. The cool cell accomplishes much of this without moving parts. Water has one particularly unusual characteristic. It reaches its maximum density not at its freezing point of 32 degrees Fahrenheit, but slightly above it, at approximately 39 degrees Fahrenheit, or 4 degrees Celsius. As water cools toward 39 degrees Fahrenheit, it contracts and becomes denser, allowing the natural convection loop to continue. But once the temperature falls below roughly 39 degrees Fahrenheit, something strange happens. The water begins expanding again and becomes lighter. Consider what that means inside the cool cell. Once the water in the radiator drops below 39 degrees Fahrenheit, it is no longer dense enough to continue sinking efficiently toward the reservoir below. The natural circulation simply begins to stop. No mechanical valve closes. No thermostat sends a command. No electrical signal is required. The system essentially shuts itself down because of the natural behavior of water. It is a form of freeze protection embedded directly in the physical structure of the hydrogen-oxygen bond. And if an extreme winter cold spell continues, the reservoir offers another layer of protection. The water eventually begins freezing from the top downward. But during the transition from liquid water to ice, it undergoes a phase change and releases an enormous amount of latent heat, about 144 BTUs for every pound of water that freezes. That stored energy acts as a powerful thermal buffer, helping keep the interior of the enclosure above freezing for days, even during a prolonged period of severe sub-zero weather. But there is one more feature attached to commercial cool cells that reveals exactly what type of customer this machine was really created for. On the side of each unit is a patented passive hydrogen vent. Lead-acid batteries can release highly explosive hydrogen gas while charging. Seal those batteries inside a tightly insulated enclosure to protect them from heat, and you risk creating something dangerously close to a bomb. Baer solved the problem using another natural physical property. Hydrogen gas is extremely light and naturally rises. His passive vent uses that buoyancy to allow hydrogen to escape safely while limiting the amount of outside heat that can leak back into the enclosure. The result is a self-contained, explosion-vented, extremely reliable steel vault that could be carried by helicopter to a remote mountain ridge and left there without attention for years. This was engineering created for a machine nobody regularly visits, located in a place where almost nobody lives. Part 5. The corporate arithmetic of cold. And that brings us back to the central mystery. The technology works. ZomeWorks manufactured it continuously for more than 2 decades. Systems based on it have helped keep telecommunications equipment operating across deserts in Africa, South America, Australia, and elsewhere. And the patents have expired. In principle, Any HVAC manufacturer could create a residential version, yet almost nobody has. To understand why, we have to stop looking only at the physics and start looking at the unforgiving arithmetic behind corporate purchasing decisions. Think about the kind of customer willing to pay for cooling that cannot be allowed to fail. A telecommunications company installs a cabinet filled with lead-acid batteries at the base of a cellular tower somewhere in the Sonoran Desert. Those batteries may be the only thing standing between a major heat wave and a dead cell site. If the batteries become too hot, their chemical lifespan can be cut in half for every 10 degrees Celsius increase in temperature. Replacing them early can cost thousands of dollars, once you account for service trucks, technician labor, specialized equipment, and travel to remote sites that may require half a day just to reach. The telecommunications operator therefore has three basic choices. Run a conventional compressor-based air conditioner from an electrical grid that may itself fail, the exact reason those backup batteries are needed. Allow the batteries to overheat and replace them repeatedly. Or purchase a heavily insulated, self-cooling steel enclosure from ZomeWorks. For the corporate customer, the calculation is easy. The buyer can estimate the return on investment almost down to the dollar before the purchase order ever reaches the supplier. The price of a cool cell can be compared directly with the predictable cost of damaged batteries and a failed cell tower. Now compare that with your house. For the average homeowner, there is no equally simple calculation. Heat is a much more diffuse problem. It arrives as a season of discomfort, an electric bill divided across 12 months, and a general desire to make the bedroom cooler. Meanwhile, sitting on the other side of the comparison is an extraordinarily powerful competitor, the conventional compressor-based mini-split. A mini-split has a recognizable model number, a written warranty, an installer who can arrive on Thursday, and a local real estate market that immediately understands what the equipment is and how it contributes to the value of the house. The residential comfort industry is built around selling complex proprietary equipment with healthy margins, followed by years of electricity consumption and an entire downstream service economy. Licensed technicians arrive during the hottest days of July to search for refrigerant leaks, replace compressors, service components, and recharge systems. A passive self-cooling steel box, filled mostly with water, has a completely different economic structure. There is little to repair, nothing to recharge. No electrical meter attached to its operation. From the perspective of building a conventional residential business, that is an extraordinarily difficult product. There is less proprietary hardware to protect, fewer components to monopolize, and above all, very little recurring revenue after the original sale. Part 6. The fatal flaw of the home version. But blaming the cool cell's absence from homes entirely on corporate greed would miss another major problem. There is a second explanation, and it is far more mechanical. It explains why the cool cell remained beside telecommunications towers instead of spreading across residential rooftops. And it contains a lesson every DIY builder, off-grid homeowner, and self-reliance enthusiast needs to understand before laying a single brick. The problem comes down to one physical law that cannot be negotiated with. Water is heavy. Remember Steve Baer's Zome house and those 90 55-gallon steel drums? Let's look at the numbers. 1 gallon of water weighs approximately 8.34 pounds. Baer had 90 drums, each containing roughly 53 gallons. That means the south wall of the house held approximately 4,770 gallons of water. Together, that water weighed close to 40,000 pounds, 20 tons, all of it standing inside the wall of a single-story private home. Baer could make that work because the drums were stacked vertically inside a wall, and a wall transfers its load downward toward a concrete foundation. A properly constructed foundation resting on solid ground can support enormous amounts of weight. But now imagine trying to apply the cool cell's sky-facing radiator concept to the roof of an ordinary house. If you want enough stored thermal capacity to cool an entire home, you need a substantial quantity of water. That leads quickly toward the concept of a roof pond. such as the system used in Harold Hayes' famous Skytherm house in Atascadero, California, during the 1970s. And this is where the mathematics becomes hostile. Only 4 inches of standing water spread across a roof weighs roughly 21 pounds per square foot. A typical modern residential roof may be framed to carry a live load of around 20 pounds per square foot. That means a surprisingly shallow layer of water, barely deep enough to become thermally useful, can consume essentially the entire live load capacity of an ordinary residential roof. Try adding that kind of system to a house that was never designed for it, and the structure can fail under the weight. So if you want a large, passive, water-based cooling system on a residential building, the structural decision has to be made before construction really begins. Before the first shovel enters the ground, before the foundation is poured, you need heavier joists, reinforced columns, and substantial load-bearing walls designed specifically to support tens of thousands of pounds of water above the living space. And for a modern production builder trying to put up 40 nearly identical suburban homes as quickly and economically as possible, that level of specialized, heavy structural engineering is an immediate obstacle. In the end, the weight of the water can settle the argument before the construction drawings are even complete. Part 7. The wider library of forgotten cooling. The cool cell is not the only example. It belongs to a much broader and surprisingly rich collection of low-tech cooling methods that have largely faded from public attention, while the global HVAC industry standardized around the electric compressor. Dig through old patent records and historical engineering journals, and you discover an entirely different world, one in which people created cold from some of the simplest and most abundant materials on Earth. Consider the unusual chemistry of zeolite. Zeolite is a naturally occurring volcanic mineral that, under a microscope, behaves almost like a stone sponge. Its rigid crystalline framework contains billions of microscopic pores and channels. Because of that internal structure, a single gram of zeolite can contain hundreds of square meters of internal surface area. And zeolite has an extraordinary appetite for water vapor. Place the mineral inside a sealed vacuum chamber with a pool of water, and it begins capturing evaporating water molecules so aggressively that it forces more water to evaporate. That rapid evaporation removes heat from the remaining liquid, lowering its temperature until it can eventually freeze into solid ice. No compressor, no moving parts, no electricity. To recharge the system, you simply apply heat. That heat can come from a solar collector or even from engine waste heat. The energy drives the captured water back out of the zeolite, restoring the material so the cooling cycle can begin again. It is a heat-driven cooling process, powered by energy we often throw away. Then there is the equally simple idea of salt-based cooling. Long before electric refrigerators existed, people were already producing ice in warm weather using endothermic chemical reactions. Certain mineral salts, including potassium chloride and ammonium chloride, absorb heat when they dissolve in water. As the crystals break apart, energy is required to separate their rigid lattice structures. The salt takes that energy directly from the surrounding water as heat, causing the mixture's temperature to fall rapidly, in some cases from room temperature to near freezing within minutes. And once the reaction is finished, the material does not necessarily have to be discarded. The saltwater brine can be poured into a shallow tray. The sun evaporates the water, leaving the dry salt crystals behind so they can be collected and used again. Even Maria Telkis, the legendary Sun Queen and one of the most important solar researchers of the 20th century, patented a building-scale air conditioning system in 1977 based on this same dissolving salt principle, designed to recharge using rooftop solar collectors. Then we come to the classic solar absorption ice maker. This is a sealed, relatively simple machine using charcoal and a small quantity of methanol maintained under a strong vacuum. During the day, sunlight heats a steel collector filled with roughly $8 worth of ordinary charcoal. As the charcoal becomes hot, it drives methanol out of the material as vapor. At night, the process reverses. The charcoal cools, and its enormous internal surface area begins absorbing the methanol vapor again. It pulls the vapor in so strongly that pressure inside the system falls. That pressure drop forces liquid methanol in the evaporator to boil at extremely low temperatures, creating enough cooling to turn a tray of water into real ice. And there is also the Mesotenko cycle, commonly called the M cycle. It is an ingenious, indirect evaporative cooling method that alternates wet and dry air passages, allowing incoming fresh air to be cooled toward its dew point without directly adding moisture to the indoor air. Each of these technologies is rooted in established thermodynamic principles. They did not disappear because they were incapable of producing cooling. They were pushed aside because many of them are remarkably simple, highly durable, and rely on materials such as stone, salt, charcoal, and water. Materials you can purchase and reuse again and again. And that places them in direct conflict with a commercial system built around selling comfort through equipment and recurring monthly electricity consumption. Part 8. Bringing the genius home. So where does that leave us? If the mainstream HVAC industry is not going to sell you a cool cell or a zeolite chiller for your bedroom, and if placing 20 tons of water on your roof is a structural nightmare, are ordinary homeowners completely powerless? Absolutely not. As self-reliant homeowners and builders, we can separate the underlying principles behind Steve Baer's work and apply those ideas in simpler, cheaper, and safer ways around our own homes. The first principle is thermal mass, and specifically, using water as thermal mass while keeping that weight firmly on the ground. You should never place a significant load of water on a raised deck or upper floor that was not designed to support it. But if your ground floor sits on a solid concrete slab, or you have a sunroom supported directly by a proper foundation, you already have an ideal platform. Heavy sealed containers of water can be positioned along a south-facing wall inside the living space. The outward-facing surfaces can be painted a dark color to absorb heat, while the sides facing the room can remain clean, bright, and reflective. During a hot summer afternoon, those containers become silent thermal sponges. They absorb excess heat from the room and slow the rise in indoor temperature. Then, as outdoor and indoor air temperatures drop overnight, the stored warmth gradually moves back out of the water. Instead of allowing the room to experience a sharp daytime temperature spike followed by an equally sharp nighttime drop, the water helps flatten that daily swing and reduces the burden placed on the cooling system. The second principle, and perhaps one of the most overlooked, is the sky radiator. A simple personal nighttime cooling experiment can be built using a shallow, dark, sealed container of water placed outdoors. But one rule controls everything: line of sight. The container needs a completely unobstructed view of the open sky. No roof overhang above it. No tree branches. No nearby wall blocking the view. On a clear, dry night, the water can radiate infrared energy through the atmosphere toward deep space and cool to a temperature measurably below the surrounding air. You can test the principle yourself with an inexpensive experiment. Take a digital thermometer with a probe and place that probe inside a sealed container of water outdoors beneath a clear view of the sky. Then place a second thermometer nearby to measure the surrounding air. Check both readings at dawn. In dry climates, you may often discover that the water has cooled several degrees below the temperature of the morning air. In other words, you have captured a free natural heat sink that has existed above your home for your entire life. To turn the idea into something more functional, you could build a small insulated box, your own miniature DIY cool cell, and use it to preserve that chilled water through part of the day. Then, a small, low-power USB fan or solar-powered fan can move air across the cool container, directing a cold breeze toward your bed or workspace during a sweltering afternoon. And in doing so, you are following the real philosophy of the ZomeWorks yard. Build a small version. Measure what happens. Keep what performs well. Discard what does not. Conclusion. Steve Baer died in May 2024 at the age of 85. For more than half a century, He spent his life arranging the natural laws of the universe into simple, elegant, self-reliant systems. The Andy Shack still stands in Albuquerque, a quiet, weathered monument to a very different way of thinking about our relationship with technology. We have built an entire civilization around complicated, fragile machines designed to fight the environment around us. Those machines demand a constant supply of electricity and chemical refrigerants just to keep us comfortable. And over time, we have become accustomed to the idea that staying cool is a service we must repeatedly purchase from a utility company, month after month. But the physical laws of the universe do not need permission from a patent office, a utility board, or a corporate executive. Water still stores heat, better than almost every common material around us. Warm water still rises without anyone telling it to. And on a clear night, the cold darkness of deep space is still there above every continent, waiting to absorb every joule of heat we can send toward it. The knowledge required to become cooler, more self-reliant, and less dependent on the electrical grid never completely vanished. It has simply been waiting for us to stop looking only at the expensive metered machines attached to our walls and start looking again at the simple, honest physics already surrounding us. So here is my challenge for you tonight. Take a dark, sealed container of water and place it outside where it has a clear, unobstructed view of the stars. Put one thermometer in the water and another beside it to measure the surrounding air. Check both temperatures at dawn. Then leave your results in the comments, along with your state or country. Let's begin building a real-world map showing just how much free natural cooling may be sitting above our heads every night. And if you want to help keep this kind of practical, self-reliant knowledge alive, the kind of knowledge that can make you a little less dependent on another monthly bill, subscribing to Survival Roots is how we continue building this library. Thank you for watching, and I'll see you in the next chapter.